So we're going to begin the mock for the April 16th exam, starting with multiple choice question 1. It asks, which will not have any effect on an SN1 reaction rate? So for this question, you have to remember all the different characteristics of an SN1 reaction, like that they're first order reaction, that they are a two-step reaction, that they prefer secondary and tertiary substrates, etc., etc. The solvent that they prefer, which is polar protic. So looking through the answer choices, it says A, primary, secondary, tertiary substrate. Well, we know that they prefer a secondary or tertiary substrate, so that does have an effect on the rate. A weakly basic leaving group is letter B's option, and the reason why this can have an effect on the rate is because if it's a strong leaving group, it's going to be easier to leave and the rate will be quicker, but if it's a weak leaving group, it won't leave as quick, which is why you have to protonate OH to make it water so that it leaves better and quicker. Looking at C, it says the high concentration of the nucleophile. Since SN1 is a first order reaction, it only depends on the concentration of your substrate, not your nucleophile. So C in this case is actually your answer because the rate for SN1 is K and substrate. SN2 is the one where it depends on the concentration of both the substrate and the nucleophile. SN1, only the substrate. Now we can look at the rest. Polar protic solvent, that does affect the rate. You do need a polar protic for SN1 reactions. And temperature. Temperature also affects the rate because generally temperature increase will also increase the rate of the reaction, but if you increase it too much, then you're going to have an elimination reaction. Okay, so number 2 asks us what is the correct IUPAC name of the compound shown. So in this case, you actually have two functional groups in your compound. You have an alcohol and an alkene, and you have two substituents, either a ethyl or a methyl, depending on how you number your chain, and a chlorine. So in this case, when you're comparing substituents, those are not going to get numerical priority. But when you're comparing functional groups, you have to think about which one is more important. So alcohols, carboxylic acids, and aldehydes all have priority numerically, like when you're numbering the chain, over alkenes. So in this case, you're going to want to number the chain 1, 2, 3, 4, and then you could either go this way or this way. The reason you're going to want to go this way is because you want to have all of your functional groups in your main chain. So even though this would give you the lower numbers, the longest chain with the lowest numbers, this will give you all of your functional groups in your main chain, which is more important. So with that in mind, you want to look at your answer choices and see which ones have your alcohol as number 2. So you can cross out E, you can cross out B, and then we can keep going. Since you have an alkene in your group, it's going to have an ENE ending, not an ANE. So ENE is for double bonds. So now we should look at our choices and see if any of them forgot to use the EN ending. And you could see that A, they did actually forget to use ENE, they used AN. So we could cross that out. Now we're comparing C and D, and it's already relatively obvious without giving the double bond E or Z designation which one's the right answer, because C numbers chlorine as number 3 and D numbers chlorine as number 5. The correct numbering would be D. So D is going to be the right answer, but just in case you guys were confused, we can go over how you can tell whether this is E or Z. So the way I personally like to do it is I like to draw in the missing hydrogens and then go from there. So on the left side, your higher priority, when I say left side, I mean this side. The left side, your higher priority is going to be your Cl. On your right side, your higher priority is going to be this whole chain. I'm so sorry. My brain gave up for a second. So this whole chain is going to be your higher priority, because when you're comparing halogens or alcohols, those are going to be number 1. But when you're just comparing two different carbon chains, you want the larger chain. So it follows the same rules as chirality. So that makes this double bond an E alkene because they're trans, which means that the higher substituents are on opposite sides, with this being the sides. This is the top half, this is the bottom half. On this side, Cl's on the bottom. On this side, the longer chain is on the top. Okay? Multiple choice 3 asks, which of the following substrates react most rapidly with tert butoxide, or T-butoxide? So the first thing you have to know to do this question is to know the structure of T-butoxide, which actually looks like this, and it is considered a big bulky base. So when you have a big bulky base, you know you're going to be doing an elimination reaction, specifically an E2 reaction. So now we can look through our choices and figure out which substrates are most favorable to an E2 reaction. E2's favorable substrates are the same thing as SN2's favorable substrates. So the more substituted leaving group is more favorable. Okay? So we can go through. The first things you can eliminate are D and E, because whenever you have a double bond right or on the same carbon as your halide, the electrons in your double bond are actually going to repel the electrons in your big bulky base, right? So E and D will never undergo an elimination reaction because these electrons are going to be repelling the tert butoxide. Okay? So you can eliminate those. And now we're going to be comparing A, B, and C. So knowing that E2 has the same favorable substrates as SN2, we're going to want to look for the more substituted option. And A is a primary one, so that's not going to be it. C is secondary, so that's okay. But B is tertiary, so B is going to be the right answer for multiple choice 3. Multiple choice 4 asks, how many transition states and intermediates occur in the reaction shown below? The only thing about this multiple choice question is that the professor actually made a mistake in the product, and instead of a Br, it was actually supposed to be a CH3. So if you struggled with this question, that's probably why, and it's probably going to be a lot easier now. So if you want to pause and try it, I more than welcome you to do so, but I'm just going to carry on because this is a YouTube video. So whenever you see how many transition states and intermediates occur in this reaction, you're going to want to draw out the entire mech. So to figure out which kind of mech this is going to follow, you want to distinguish what kind of reaction it is. So you see Br is a good leaving group, and you see that you have a polar protic solvent, H2O, which can also act as a nucleophile. So most likely this is going to be an SN1 reaction. So let's get started with the mech, which I'm sure you have done a million times by now. The first step is going to be Br popping off, leaving a carbocation behind. And because a more stable carbocation can be formed in this situation, that there's going to be a hydride shift. So this H is going to shift. I'll do that in the next step though. Okay. Hydride shift. And that will give you your more stable carbocation intermediate. And then moving along, now your nucleophile, H2O, is going to attack. Oops. Okay. And for the last step, you're going to deprotonate your H2O because you don't want it to stay that way because H2O is a good leaving group, so it'll pop back off. You have to deprotonate it and turn it into OH. So another H2O is going to come in, or the Br, whatever, doesn't matter. It's going to come in and pull the H off. And then you're going to get your final product. H plus just means acid. It's the shorthand for H3O plus. Okay, so with this in mind, we can now look at the question and decide how many transition states are and how many intermediates there are. So transition states are going to be representative of each of the steps that you do in the reaction, and the intermediates are going to be the literal intermediates, so not the starting reagent or the ending product, but the intermediates in between your reactions. So each step, like I said, is going to be a transition state. So 1, 2, 3, 4. So right off the bat, you know that your answer is going to have 4 transition states, and the only answer with that is B. So B is going to be your right answer for number 4. But just to show you, here are your 3 intermediates, because these are not the starting material and these are not the ending, they're the intermediate. So multiple choice 5 asks, which is the correct rate equation for the reaction shown? So in general, you're probably going to be comparing SN1 and SN2 reactions in these cases. So it's important to memorize the rate laws for both SN1 and SN2 reactions. So the rate law for SN1 is rate equals K times substrate. Substrate is the same thing as alkyl halide. SN2 is rate equals K times substrate, I'm going to abbreviate that as subs, times nucleophile. Okay, the easy way to remember this is that SN1 is first order, meaning it only depends on the concentration of 1, and SN2 is second order, so it depends on the concentration of 2 different things. So now, looking at multiple choice 5, we can distinguish whether this is an SN1 or an SN2 reaction, and then we can just pick the answer because we memorized the rate laws. So the first thing you want to look at is whether the alkyl halide is primary, secondary, or tertiary. In this case, we have a primary alkyl halide. So that, as we remember, is representative of an SN2 reaction. But that alone isn't enough. We want to check the solvent and the nucleophile as well. So the solvent is acetonitrile. So I'll write that down. And that is a polar aprotic solvent. And as we remember, polar aprotic solvents are characteristics of, again, SN2 reactions. And now looking at the nucleophile, we can see that with a negative charge, it's going to be a really good base, which means it's a strong nucleophile, which is also representative of SN2 reactions. So now that we know this reaction is SN2, because we have 3 different things supporting that, we can go and try to find the rate law for SN2 in the answer choices. So A is incorrect. This isn't the rate law for any of them. B is the rate law for SN2 because it is rate equals K times substrate times nucleophile. Like I said, alkyl halide and substrate are the same thing. So the answer to multiple choice 5 is going to Multiple choice 6 asks, which compound would have the most endothermic heat of formation, which is represented by delta G of F. So when you're thinking of heat of formation, the least stable a molecule is, the higher the heat of formation is going to be, or the more endothermic the heat of formation is going to be, because it needs a lot more energy to form unstable bonds. So I'm going to write that down. The least stable molecules have the highest heat, or most endothermic, I should say. The most endothermic heats of formation because it takes more energy, which we all know heat is a form of energy, to form unstable bonds. So all this question is really asking us is which of these molecules is the least stable, and as you guys can probably figure out very easily, it's going to be C, because even 4-membered rings are unstable, 3-membered rings are almost unheard of. So the answer to multiple choice 6 is going to be C. Multiple choice 7. Multiple choice 7 asks, a sample of a chiral compound consists of 40% of the S enantiomer and 60% of the R enantiomer. The sample has an observed optical rotation of plus 12 degrees. What is the specific rotation of the S enantiomer? Okay, so these kinds of questions, I remember him saying he wasn't going to put on exam 1 and that he was going to move it to exam 2, but he also said that way many months ago, so I'm not sure if he's planning on putting this question on your exam or not. But either way, it's not difficult to go over, so we might as well just do it. So the way you get the sign of the specific rotation of S is by looking at the data that they give you. So they tell you that you have 40% S, so that means you have less S, and you have 60% R, so there's more R, and the sample has an observed optical rotation of plus 12. So that means that R has to be the positive one and S has to be the negative, because S and R are going to both have opposite signs, right? So the way that you set up the equation if you're trying to find the specific rotation of the minority is you want to do the majority minus the minority over 100, set that equal to the specific rotation of the entire thing, which in this case is plus 12, and then you want to write X underneath. And this is going to be the specific rotation of pure S, or pure the minority, whichever it is. Okay? So then you want to do 60 minus 40 is 20 over 100, and that gives you 1/5. Set that equal to 12 over X. 1 times X is X. 5 times 12 is 60. So X equals 60. So this means the rotation of S is 60. And since we already designated that it's going to be negative, this gives you the answer negative 60 degrees. Quickly, before I forget, I realized I didn't say this. If S is negative 60, that means R is going to be positive 60. They're always opposite of each other. So if S was negative 40, then R is going to be positive 40. Okay? So technically, I did say this is the minority, but it could also be the majority. You just have to make sure you get your signs correct. And the only way you can get your signs is by just reasoning through it. The equation itself isn't going to give you the sign. And that's all for this. Multiple choice 8 asks to rank the following alkenes in order of increasing heat of hydrogenation, with the least exothermic first and the most exothermic last. So this is a kind of repeat question similar to the pre-mock. It's not the same question, but similar. So the more stable you are, alright, you know what, I'm not going to use arrows. More stable equals lower heat of hydrogenation, which also equals the least exothermic. Reason being is that more unstable molecules release a lot of energy when they break up. Alrighty. So, let's first look for the most stable one. When you're looking at comparing different types of double bonds, you want to look at first how highly substituted it is. So number 1, how substituted the double bond is with more substituents creating a more stable double bond. So, first I'm going to go through the answer choices and look to see which one's the most substituted. Number 1 has carbon coming off here, 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 and here. So it has carbons coming off on all sides. So that's really, really substituted, and that's probably going to be our number 1. Because it is the most substituted, but we'll keep going. Number 2 has 2 H's and 2 carbons, so that's okay. 3 is terminal, so this is usually pretty bad, less stable. 4 has 2 carbons and 2 H's, just like 2, except it's a cis bond. 5 has 3 carbons and 1 H. So that being said, 1 has the most carbon chains or carbons coming off of it. So 1 is going to be our most stable and have our lowest heat of hydrogenation. So you could eliminate any of the answer choices that don't have 1 as the first one. And then after that, 5 had 3 carbons or carbon chains coming off of it. So that's going to be your next most stable. So that doesn't actually eliminate anything. Your least stable is going to be number 3 because it's terminal. So it only has 1 carbon or 1 carbon chain coming off of it, which is this one. And it has 3 H's coming off, which is not good. So 3 has to be at the end, and both A and C, 3 is at the end. So what they're trying to get at here is they want you to be able to compare cis and trans double bonds. So cis double bonds or Z double bonds are less stable than E or trans double bonds. Now, that being said, we can go back and we can see that since 2 is trans, it's going to be more stable and have a lower heat of hydrogenation than 4. So the answer to multiple choice 8 is going to be C. So multiple choice 9 asks, which set of reagents will yield the same product with each of the alkenes shown? So what they're asking is which set of reagents can you use on both the first and the second reagent, or the first and second double bonds, to get the same product. So first things first, you want to understand what each of the reagents do. I think the only mechanism I haven't drawn out for you guys is the HBr over CH2Cl2. So what this does, HBr CH2Cl2, it's going to protonate the protonate the less substituted end of the double bond. Oops. Why is it not erasing? And it's going to leave a carbocation at the more substituted position, which the Br is going to add to. Okay, so Br, oops. Br adds to the more substituted side. So multiple choice 10 asks, which of the following solvents will favor the SN2 reaction shown? So all you have to, honestly, the reaction doesn't really matter that they give it to you. All you have to know about this is that SN2 reactions favor polar aprotic solvents. And then you have to know what they are and what their structures are. Okay? So I'll give you my list, which I've already done a couple times, but, you know, the more the merrier. So there's DMSO, there's DMF, there is acetonitrile, there's acetone, oops, acetone, and there is THF. Okay, with all of these in mind, we can go and look at our answers. So number 1 is the structure of DMSO, and we know that's a polar aprotic one, so this is going to be one of your answers. Number 2 is not one of our polar aprotic solvents. In general, alcohols are not going to be polar aprotic. There would be more on the polar protic side. Polar aprotic means that you don't have any protons or hydrogens to donate. So in general, it's not going to be anything acidic. Number 3 is a polar protic solvent that we see in SN1 reactions. Number 4 is the structure of acetonitrile. It's just the shortened version. So 1 and 4 are looking pretty good. 5 is not one of our polar aprotics, and 6 is not polar at all. So the answer to number 10 is going to be 1 and 4. Okay, so number 11 says what is the major product of the reaction shown? So the reaction shows a elimination reaction with CH3O- and heat, specifically an E2 reaction. So you know that you need to have your Br antiperiplanar to your H. And a little trick for these, if your Br is on a dash and your H is also on a dash, they are anti to each other. So in this one, you actually don't have to draw the Newmans out, because if you remember that little hint, you're going to know that all you have to do is just eliminate the 2 and add a double bond in their place. And if you keep the molecule exactly the same, adding a double bond, you see that your answer is going to be D, because the ethyl is going to stay up here, the carbon down here, this ethyl is going to stay down here, and the carbon up there. Okay? Multiple choice 12 asks, which of the following would increase the rate of the reaction shown below? So the first step you have to do is to figure out whether this is an SN1, SN2, E1, or E2, and then draw the rate of the reaction. So the fact that they give you NaOH shows that you have a strong nucleophile, OH-. And that is going to give you the hint that this is an SN2 reaction. Not to mention, you have your polar aprotic solvent, DMSO. So we can go ahead and draw the rate law for that. So rate equals K times substrate times nucleophile. So the things that would increase the rate in this situation, oopsie, how does it do that? So the things that would increase the rate in this situation would be either increasing the concentration of your substrate or increasing concentration of your nucleophile. So these would increase rate. There's 2 different ways. So now, with this in mind, we can go through the answer choices and figure out which of these can actually increase the rate. So, decreasing the concentration of the alkyl halide is what A says, and that's incorrect because that would decrease the rate. So you can go ahead and cross off A. Changing the solvent from DMSO to ethanol, that's incorrect because ethanol is polar protic. So that would also decrease the rate. Anything that is taking away from what SN2 wants is not going to increase the rate of the reaction. It needs favorable conditions to have a faster rate of reaction. Increasing the concentration of NaOH. So NaOH in this situation is going to be your nucleophile. So increasing the concentration of NaOH does in fact increase your rate of reaction. So the answer to this question is going to be C, but we can go through the rest. Changing the leaving group from Cl to F, this is actually not going to increase the rate of reaction because Cl is a better leaving group than F. And you guys can check his notes for his little list of increasing leaving group. I'm pretty sure Br is the best, then Cl, then F, then I. But definitely double check that one. It is definitely in his notes. So changing the nucleophile from OH to H2O, that again is basically changing it to a SN1 favorability. So that's not going to help an SN2 reaction, that would help an SN1 reaction. So anything that is deviating from what SN2 normally is not going to increase your rate, it's going to decrease it. So E and D are not your answers. And C is your answer. Multiple choice 13 asks, which of the following reactions is most likely to produce the major product shown? So the best way to do this is to just go through this one by one. So A shows you a molecule and then an SN2 reaction, but the issue is that it gives you the elimination product. If this were to be an elimination reaction, you would have had to write heat, but because they didn't, this is not going to give you that as a major product. Instead, it will give you the SN2 product. Okay? So moving on to B, I know you guys haven't seen this one yet, but when you treat the double BRs with NH2, you're going to get one double bond in between them, not two double bonds away from each other. So that is not correct. Looking at C, we can see this is a big bulky base. I'm not sure why they didn't include heat here, but they definitely should have. But in general, when you have a big bulky base, the only thing you can do is elimination, so sometimes they won't include heat. But in more recent years, his exams, they usually put both. But in general, when you see a big bulky base, just know the only thing it can do is elimination because it physically cannot attack a carbocation to do an SN2 reaction. Okay, so looking at C, when we're thinking about tert butoxide and an E2 reaction, you're going to get the less substituted double bond product. So if this was an E1 reaction, you would have the more substituted one. Since this is an E2 reaction, you're going to have the less substituted double bond. And that's exactly what they show in the product. So your answer for number 13 is going to be C. But we'll keep moving just to go through the rest. So D, okay, so D is all kinds of a mess. You start with Br and you have H2O. H2O is a SN1 reaction solvent. I'm sorry, my brain is giving up in life. But yeah, it's a polar protic solvent and they're giving you an elimination product. The only way you're going to get the elimination reaction is if you also added heat. So this is not going to give you the elimination product as your major product. It would give you the SN1 product as your major product. So that's not going to be it. And E has tert butoxide again. You don't need to put heat in this one because the only thing tert butoxide can do is eliminate. It can't attack in any way. But heat does increase the rate of the reaction and the formation of the product. So typically O'Connor will put it. Anyways, so tert butoxide eliminates Br, leaving a double bond behind in the less substituted side. In this case, we have your double bond on the more substituted side when really it should have been here. So this is not going to be your answer to number 13. Multiple choice 14 asks, what is a likely product of the reaction shown? So although we've never seen, or at least I don't think you guys have ever seen, Br2 over CH3OH, it's actually going to act in the exact same way as Br2 over H2O. So what this means is that you're going to have the ringed intermediate with Br, and that like H2O, CH3OH is going to come and attack the more substituted side, and that is going to make sure that there's anti-addition between the Br and the CH3OH. So what that means is that one of them is going to be on a wedge and one is going to be on the dash. They are not going to both be on wedges or both be on dashes. Okay? And another thing that means is that there's going to be no carbocation intermediate, so you're not going to have any rearrangements in this product. So looking at the answer choices right off the bat, you can eliminate anything that incorporates this answer. That incorporates this carbon or changes anything about that carbon, because in this mechanism, the only things that are going to interact are these two carbons here. So we can eliminate A because the Br is not going to add up there. It's going to only add across this bond. You can eliminate B because, again, there's going to be no shifting and there's no way that the CH3OH would add up here. Okay? And yeah, so you can only eliminate A and B. And you don't even have to do the whole mechanism to figure that part out, okay? So let's get started with the actual mech. Okay. So the first step is going to be the electrons coming and picking up one of the BRs, and then the rest of the electrons are going to move to the subsequent BR. And in this case, I'm going to draw the ring on dashes. It doesn't matter because technically you're going to get both mixes anyway. So if you want, you could put it on wedges. That's also correct. Okay. And then you're going to have the Br anion. Okay. And the next step is going to be the CH3OH coming in and attacking the more substituted side. So going to attack here, and it's going to push the CH3 down to a dash. Had the CH3 been on a dash already, it would push it to a wedge. So it's going to invert the stereochem of whatever is already on that carbon, and it's going to kick the Br off. Okay? And then the last step is going to be deprotonation, which you guys should know. Either water or the Br anion comes and pulls this off. Oh, technically I did not draw that right. It's not going to obviously, it's not going to bond on the carbon side. It's going to bond on the O side. So it's supposed to look like this, if you're getting specific. So yeah, the last step is going to be deprotonating it. And then your product is going to look like this. And then obviously you're going to have the exact opposite, where every stereo center except this one is going to be opposite, because this one plays no part in the reaction. So now we could look at the answer choices and try and see if that is one of the choices. And actually right away, I can see that E is one of the choices, because you have the Br and the CH3 syn to each other, which means they're both on dashes, and you have the Br trans to the OCH3, which gives you the right answer for number 14. Okay, so number 15 says, which of the following reactions will result in the formation of a meso compound as a major product? So the best way to do these is to be able to recognize what the reagents do and then just draw the product right in there, similar to like a box problem. But for the sake of this mock, I'll go in and draw the mech. So for this one, you're going to have Br2, so you're going to have two Brs adding anti to each other, right? So Br2 over CH2Cl2. The first step is going to be the electrons coming and attacking one of the Brs. Okay. In this case, I'm just going to put it on a dash again. Doesn't matter. And then the second Br is going to attack either side of this ring. I'm going to pick up here, and it's going to attack on a opposite stereochemistry from the original Br. And that gives you Br on a wedge and Br on a dash. So now we can try to assign stereochem. So the way I'm going to do that is like this. Okay, so we want it to be a meso compound. Just a refresher of what a meso compound is. It's a cyclic compound usually with a plane of symmetry, and you're going to have one R stereocenter and one S stereocenter. Okay, so the Br is obviously going to be number 1, number 2, number 3. So this is S, but it is really R because you have to switch it since the Br is on a dash. So this one's R. This one's going to be number 1, this one's going to be 2, and this one is 3. So this one is also R. So this one is not going to be the meso compound, and we can move along. I'm just double checking my work really quickly. Yes. Okay. The next one, H2PT, although they don't make you memorize the mech, the only thing that this does is it adds syn hydrogens over across a double bond. So this means the hydrogens are going to add at the same stereochemistry. They're either going to be both dashes or both wedges. I usually see them drawn as both dashes. But the final compound is not even going to have chiral centers because it's going to look like this. So it's definitely not B, and it's not A. can keep going. The next one is Cl2 over CH2Cl2. And this one is going to add 2 Cl's across either side of the double bond trans to each other. Okay? Ooh, let me count my carbons. Okay. I'm just shorthanding these mechs now because by now you should definitely know them like clockwork. Oh, I missed a carbon here. So this one's going to be on a wedge, and this one's going to be on a dash. So now we can go ahead and assign stereochem. So this is going to be 1, 2, 3. So this one is S, and this one is going to be 1. Oh, let me do it in a different color. 1, 2, 3. So this one is S, but it's actually R because you have to flip the stereochem. And because there is a plane of symmetry down this molecule, this is a meso compound. Okay? So the answer to number 15 is going to be C. But taking a second to look at letter D, the HgCH3COO minus is the exact same thing as HgOAC. So just so you guys know, this is still the oxymerc reaction. And as you guys know, it's going to add Markovnikov addition without a rearrangement, but you're going to get a mixture of products. You're going to get it added both on a dash and a wedge. So in this case, since both of these carbons are equivalent, it doesn't matter which side you put the OH on. But at one point, you will have the meso compound, which is if you put the OH on a wedge. So I'm going to go ahead and show that. 1, 2, 3. So this is R. 1, 2, 3. So this one is S. Reason that this is not the answer, and this is a very tricky and important point, is because 15 asks you which will result in the formation of a meso compound as a major product. So this is going to be a 50-50 product. However, C, the only compound or the only product that you're going to get is the meso compound. So you're going to get 100% meso here versus 50% meso here. So that is why D is not the answer to 15. So multiple choice 16 asks to rank the following carbocations in order of decreasing stability. So that it means the most stable is going to come first. Okay? So you guys should be very comfortable by now with ranking the stability of carbocations, but we're still going to go through the rules. And I actually think this question brings up a really interesting point with option number 2. Okay? So very first thing you want to look at is how substituted is the carbocation. Okay? So primary carbocations are going to be the least stable and the least substituted, and it's just going to be bonded to one carbon. Secondary carbocations are going to be medium stability, and tertiary carbocations bonded to 3 carbons are going to be your most stable. The next thing you should look at is resonance. Can a lone pair or double bond resonate with the carbocation? Oops. Okay, it doesn't want me to put the end in. All right, so obviously if resonance is possible, that's going to help the stability of the carbocation. But in number 2, they actually show you a carbocation on a double bond, which is very, very unlikely to happen because the double bond is going to move right over. So this is actually going to be your least stable molecule here. It's something that most people probably have never seen before, so it's totally cool if you were confused about it. You could actually figure out the answer by going through the others anyway. But number 2, just so you guys know, is going to be your least stable. You will never see this sort of situation in real life. Okay, Now, say we didn't know that. Say we weren't sure, because most likely on an exam, it's high pressure, you're not going to be completely thinking straight. Let's look through the rest of the choices that they give us. So the first thing we want to look for are the ones that are tertiary carbocations. And we can see that both 1 and 3 are tertiary. But what are the differences between these two, right? So 1 is actually conjugated, or that means it has resonance because there are double bonds nearby. So these double bonds can actually come out, even though it's very unlikely because double bonds like to be in rings, they have the opportunity to come out and resonate and get rid of that carbocation, at least in this section. It would move it over here, right? So they can resonate with the carbocation, which at the end of the day, even if it's an unlikely resonance, it's still going to increase stability. So number 1 is going to be more favorable than number 3. So you can cross out any of the answer choices where number 1 is not first. So that's A, C, and E. And now you can see that 3 is the only tertiary one left. So the next thing is going to be 1, then 3, right? So the only answer choice with that is D, and that pretty much gives you your answer. But we can go through the rest. So tertiary first, we did that. 1 and 3 are the tertiary ones. Now we're going to compare the secondary ones. So there's 4, 5, and 2. 4 is the most stable secondary one because this double bond can come and resonate here, which we see in our answer choice. So that makes sense. 5 is our next most stable, and then our least stable is this one. And this is just kind of one of those fun fact ones that you probably haven't seen before, but you didn't need to know that 2 was the least stable to answer this question. Okay? So number 17 doesn't really ask you a question, but they just ask you to find the product to the following reaction. And this one is relatively simple because they don't include heat, and almost all of these products are potential elimination products. So because they don't include heat, you know this is either going to be SN1 or SN2. And because this is a strong nucleophile, anytime you see an Na, you know Na plus is going to be paired with, is going to be paired with an anion. So that means your OCH3 is in its anionic form, and it's going to attack and kick the Br off in a SN2 reaction. Although they don't give you the polar aprotic solvent in the reaction arrow, you don't need it to know that this is an SN2 reaction. So your answer to this one is going to be C. The other weird thing about this question is that they don't have the stereochem in the initial reagent, so you're not going to put stereochem in your product because you don't know what the inversion is going to end up as. So yeah, 17 was a little bit of a weird one, but it's also, I think, one of the easier ones on this mock exam. Okay, so 18 asks, how many of the following changes would make the rate of this reaction go faster? And addressing leaving groups, I actually did look into it really quickly. I went to find my notes. So this is the order of leaving group ability. So I is going to be your best, then Br, then Cl, and then F. So just remember that and you'll be good to go. Okay? So number 1 says changing Br to Cl. So changing a good leaving group to a not as good leaving group is actually going to make the rate of your reaction go slower. So that is not one of our answers. Changing Br to I, so changing a good leaving group to an even better leaving group, will increase the rate of your reaction. So 2 is one of these that are true, or that do make the rate of the reaction go faster. Number 3 says increasing the concentration of R2 bromobutane. Okay, so for this kind of statement, they're asking you whether this is a SN1 or SN2 reaction. So this is pretty easy to figure out because you see an inversion in your product. So that is the most obvious way of being able to tell that this is SN2. Also, SH is negative. It's in its anionic form because you see the Na plus is paired with it. So that also tells you that it's SN2. I know you see H2O as a polar protic solvent. However, sometimes people include H2O under the arrow as a way of saying this is a counterion that is formed throughout the reaction. So don't worry too much about the H2O. Focus more on the nucleophile and the stereochem, and you'll be able to address which reaction it is really, really easily. So number 3 says increasing the concentration of R-bromobutane. Okay, SN2 reactions, the rate depends on the nucleophile and the substrate. So yeah, that actually would help the reaction because you're increasing the concentration of the substrate, and that's going to increase your rate. Okay, now increasing the concentration of water. This is pretty much useless. You wouldn't want more polar protic solvent in an SN2 reaction, so that is going to decrease your rate, and that's bad. Okay. Number 5 says increase the concentration of sodium hydrosulfide. So this is your nucleophile. This is this that they're referring to. And as you can see from your rate law, increasing the rate of your nucleophile is going to increase the rate of your reaction. So this is good. Okay. Changing water to methanol. So no, that is not going to increase the rate of your reaction because you're changing a polar protic solvent to an even more polar protic solvent. So this is bad. Methanol is more likely to donate protons than water will because it's more acidic. 7 is changing water to DMF. That's what dimethylformide is, so DMF. And as you guys know, that's one of our polar aprotic solvents, and that will increase the rate of the reaction because SN2 prefers polar aprotic. So 4 of these would make the rate of reaction go faster, so the answer to number 18 is going to be C. Okay, so number 19 says, in the reaction shown below, indicate whether the reaction rate will increase under the conditions listed in X, Y, and Z. So very similarly to what we did to the last question, you want to distinguish whether this is an SN1, SN2, E1, or E2 reaction, right? So we're going to first compare the reagent and the products. So we see that we start with our Cl, our leaving group, on a wedge, and we finish with our nucleophile being added on a dash. Not to mention, it's the only major product. So when you get inversion and only one product, that is characteristic of SN2 reactions. To strengthen the support that this is an SN2 reaction, you have a strong anionic nucleophile and a polar aprotic solvent. So this is an SN2 reaction for sure. Okay, so now we can look at the conditions and see whether or not this would increase the rate or decrease the rate of reaction for an SN2. So increasing the amount of DMSO solvent, that's going to increase the rate of reaction because you're giving more polar aprotic solvent. So you can eliminate anything where it says that X will decrease the rate of reaction. Oops. So eliminate B, D, and E. Okay. Y says change the solvent from DMSO to ethanol. So you're going from polar aprotic, which is characteristic of SN2, to a polar protic, which is characteristic of SN1. So that is definitely going to decrease the rate of your SN2 reaction. So right off the bat, you can eliminate C, and the answer is A. So you don't really, for this question specifically, you don't have to remember which of the leaving groups is better, but just a reminder that I is the best, then Br, then Cl, then F, okay? So the answer to number 19 is going to be A. Okay, multiple choice 20 asks us to rank the following by increasing leaving ability. So when you're looking for leaving ability, conjugates of strong acids are the best leaving groups. Okay, so with that in mind, we can actually just go straight through this question. So the strongest acid conjugate here is going to be HBr. So that means Br is going to be the best leaving group. The next strongest acid is HF. So F is going to be the next leaving group because these are all part of the 7 strong acids. The next strongest acid conjugate is going to be H3O+, which is the conjugate of H2O. So H2O is next. OH is the conjugate of H2O, and H2O is relatively neutral. So OH is not going to be that good of a leaving group because its conjugate acid is neutral. NH2 is the conjugate acid of a base. So that's going to be the worst leaving group. Okay? So you want the conjugates of the strong acids as the best leaving groups, right? And the conjugate of the worst acids or bases or neutral at the bottom. So that's the answer to 20. Technically, I should have given the letters. So it's B, E, D, C, A. Okay. Multiple choice 21 asks, if each compound is treated with the same reagents, which reagent will create two different compounds, but that's the same thing as saying two different products. So it's similar to the question that we did before, but they wanted two different compounds with this creating the same product. Now we have two different compounds with two different products. So just make sure that you read the questions carefully because they could ask you the same question in different ways. Okay, so I'm going to call this alkene 1 and this alkene 2, and we're going to go through and just treat them with all of the different reagents. So alkene 1 with A. Okay. So really quickly, you want to think in your head what HBr does before you even start, right? So the electrons are going to attack the H from HBr, and it's going to protonate the less substituted side, leaving behind a carbocation. This opens up an opportunity for shifts. And then the Br is eventually going to attack the carbocation, okay? So I'll give you the mech, but just so you guys know, you should be thinking about what is going on before you even put the answers. So we're going to protonate the less substituted side, leaving a carbocation on the more substituted side. And in this case, there's not going to be any hydride shifts because that is the most stable carbocation you can get here. So then you're going to add the Br anion, and that is going to attach here. So your product for 1A is going to be this, okay? So now let's try with 1B. Okay, so we're going to protonate the less substituted side, and the carbocation is going to be here. In this case, you're going to have a hydride shift. Okay, and the carbocation will move here. Now the Br is going to attach, and that is going to give you the same product as 1A. So this is alkene 1 with A's reagents, and this is alkene 2 with A's reagents, and you get the same product. So that's not what they're looking for. They want different products, so you can eliminate any answer that has A in it. So that's 1, 3, 5, and 6. So now we're between 2 and 4. And if I was taking the exam at this point, I would do D with both of the alkenes to save time, and that way you could figure out which one is the right answer right away. But we'll go through them all one by one just because repetition. So B, thinking about what it's going to do before we do it, is going to give you an OH with a possibility for a hydride shift, right? I actually don't feel like doing the whole mech for this one because H2SO4, I'm pretty sure, is a mech that you guys don't need to memorize. So I'm just going to give you the carbocation intermediate. And then the OH is going to add, well, technically the H2O is going to add, but it's going to deprotonate. So HOH, deprotonate, boom. And you're going to get the same product doing the other one because this is a reaction that allows for rearrangements. At this point, you could pretty much look at the reagents and see if any of them allow for rearrangement, then you're going to get the same product. Okay. So you're going to have the carbocation here. You're going to have the hydride shift. The carbocation will form here. Water is going to attack. And then you're going to deprotonate it. And boom, you have the same answer again. So obviously B is not going to be it. So not B, not A. C is another mech you guys don't need to know. It's oxymercuration. And this is going to give you the Markovnikov product without rearrangement. Okay. Although you already know this is going to give you the right answer because it's in the only two that you have left, we'll just go through it. So Markovnikov product means you're going to add to the more substituted side, and it's going to add an OH. So you're going to get this. This is again going to add to the more substituted side, and it's going to add an OH, no rearrangement. So these are not the same compound. That's supposed to be an equal sign with a slash through it. So these are not the same compound, so C is definitely going to be one of your answers. Okay. Now D, Br2 over ethoxide is the exact same thing as what we were doing before with the H2O. So you're going to have the ring formed. I'll put it on dashes. Br. Then the ethoxide is going to attack the more substituted side. So ETO is going to attack here. It's going to end up on a wedge. ETO. And the Br is going to end up on a dash down here. Now doing this again with the other one. This is not like a full and complete mech. I'm obviously shorthanding it, but we've done this so many times that I feel like you guys are probably getting tired of me repeating it. And if not, you could always ask, oops, I drew the ring in the wrong place. It's supposed to be here. Okay, so now the other Br is, or the ethoxide is going to attack the more substituted side. Wow, okay, I'm really just messing up here. The ethoxide is going to attack the more substituted side, and that's going to give you, I'm running out of space. Br on a dash, and ethoxide on a wedge. And you can see that these are not the same. So the answer is going to be 2CND, but we'll keep going. I think the only thing left is H2PT. And you guys know by now that that just changes a double bond to a single bond. It just adds two H's. So both of the products, if you got rid of the double bonds, would be exactly the same. Because this one becomes this one becomes this one. So that one's relatively easy. And the answer is 2, because I guess this one didn't get a letter. Okay, so I realized after looking at this a second time that you guys can't do the first half of F. You guys don't know the reaction for that yet. So apologies on that. I'm going to go ahead and get rid of it and give you the starting reagent that would give you that product, or that could give you that product. So 1 second. Okay. So I want you to try F again, but with this as the starting reagent, and see if you can get the answer. If you want, go ahead and pause. But I'm just going to go over it anyway, since this is a video. So the trick to this question is noticing that your double bond is going to be least substituted. So the way to get a elimination of an OH with a double bond that is least substituted is using an E2 reaction. So you're going to need tert butoxide, its counter ion, Na, to balance it out, and heat, and that's how you get that. The next one is going from OH to another least substituted double bond. So in this case, you could use POCl3, or you can again use a big bulky base, totally up to you. Actually, can you use a big bulky base because the OH is terminal? I would say for terminal OHs, stick with POCl3, because the thing with big bulky bases, right, they're pulling off the terminal hydrogen. So in this case, it may be difficult for them to pull off this hydrogen. So I would say stick with POCl3 as an elimination of terminal OHs, okay? So POCl3 over pyridine, you could either draw it or write PYR. So if you see PYR, know that that means pyridine. The last one is probably the hardest one, if you guys were maybe going quickly, because what this one actually is as you can see, the strong nucleophile, the good leaving group, and the polar aprotic solvent. This is an intramolecular SN2 reaction, okay? So what that means is it's actually going to attack itself and form a ring. And if this was something you struggled on, like, don't worry about it, because at least now you see it for the exam and you won't get tricked. So this is going to attack this carbon and kick off the BR, forming a 6-membered ring. 1, 2, 3, 4, 5, 6, where one of them is the O. And then you're going to have a ketone off of carbon 5. So that is the answer to H. Okay. So in letter G, this brings up a really important point that I wanted to make sure you guys don't forget your oxidizing and reduction reactions. So going from a ketone to an OH using NaBH4, or going from an OH to a ketone using maybe K2Cr2O7, going from a OH to a carboxylic acid. Make sure you don't forget those reactions. I know we went over a long time ago, but they're still important. So the first step, looking at the product, you know that you're going to have, or you're going to need an OH that is going to get oxidized to a ketone. So now you start with a double bond. So how can you get a OH on there? Specifically added Markovnikov style. So it's added to the more substituted side. I always like to use, when I'm doing box problems, I like to use things that won't give me rearrangements unless I need them. Technically, it doesn't matter because you won't get a rearrangement in this case anyway, but I still prefer to do the Markovnikov without rearrangement. So the only reaction that does that is the oxymercuration reaction. So the first step is HgOAC2, and then THF and H2O. The second step is NaBH4 and ethanol. And that is going to give you your Markovnikov OH without rearrangement. Now you want to oxidize it, and I'm going to use K2Cr2O7, but there are multiple ways to oxidize something, and that will give you your ketone. Okay, so moving on to this mech. Again, I'm going to draw this mech with all of the lone pairs and all of the arrows so you know exactly what they would be expecting or what it's supposed to look like. Okay, so the electrons from the double bond are going to pull the H, and the H is going to protonate the less substituted side of the double bond. This step is reversible. Ignore my dog snoring in the back. And you're going to have your Br counter ion. Okay. And as you can see, in this case, there's going to be a shift, but since there's no hydrogens to shift, you're going to actually have a methyl shift in this question. So that's going to be this step. And this is not reversible. And the final step is going to be the Br coming and attacking your counter ion. I'm sorry, cation. Finally is a review of a mechanism that we have done many, many times, but it's worth going over just so you guys don't forget it. So I'm going to be doing this mechanism in full with all of the lone pairs and correct arrows. Okay. Give me 1 second. Sorry if you can hear my dog in the background. Okay, so the electrons from the double bond are going to pick up the first Br. This is going to move the electrons to the second, and you're going to get the ring structure around 1 Br. I'm going to put them on dashes. You could put it on wedges too. They're both right. And the counter ion. Okay. So in this case, the H2O is going to attack the more substituted side of the ring. I'm running out of space, which is why I'm starting to write smaller. Again, sorry if you can hear my dog. So it's going to attack from up here, and this is going to swap the stereochemistry of the methyl and move the Br over. Okay. So now the methyl is going to be on a dash. Your protonated OH is going to be on a wedge. And all right, the lone pairs were I tried to squeeze them in there, but that's not very good. So I'm going to draw them a little further, and a Br is going to be on a dash here. So the last step is deprotonating your OH, like so. I'm going to use the Br counter ion. Doesn't matter which one you use, whether you use water or that. Okay. And then the electrons go into it. Sorry, I'm running out of space. And this is your final product. Okay. You could say plus an enantiomer in this case, since you have to do it both ways. And that's it for the mock exam. Congrats on finishing it. This is definitely longer than your real exam. I heard your real exam is only 20 multiple choice. I think I put like 21 and then a bunch of open-ended. So good job on finishing this, and I'm sure you guys will do really well if you did both the pre-mock and this and look at the old exams. Specifically, there was a 2006 old exam 3 and final exam that I thought was worth looking at, but the printer quality was really bad, so I didn't want to put it as a mock. But I thought the questions were pretty good. Okay, feel free to ask me questions in the chat. Bye.